we're going to do section 4.5, the derivatives and the shape of a graph. That is on page 390. Now, the first we need to remember is that corollary 3 from the previous section, where it says that for increasing and decreasing functions, in corollary 3, we basically learned that if f prime is bigger than 0, then f is increasing. That's my personal symbol to mean increasing. And then and f prime is less than 0, then f is decreasing. Roughly, that's so that's what we remember from corollary 3 from the previous section. Now, from that piece of information, we know that in that case, combining with what we know earlier, that is at the critical point, f prime equal to 0. So anytime you have, let's say, a maximum, right, then you know that f prime must have gone, say here's a maximum, then f prime must have gone from going bigger than 0 to equal to 0, and then to less than 0. That is that's how you know that you have a maximum. And also, if you have a critical point, similarly, if you have a critical point right here, that's your critical point. So then you know that f prime becomes, from this side, it is first is less than 0, okay, the slope down, and then it became 0, and then it becomes bigger than 0 on this side. And if you know that, if you find that out, then you know you have a local minimum. And this information is only for some area that's right next to the point in question, our critical point, where f prime is 0. So then you check the things close to it, and then you notice if they're both, if one goes from bigger than 0 to less than 0, that means it's a local maximum. And similarly, the other way means it's a local minimum. Now let's look at the graphs. The example on the following page 391, there's a graph here that I would like you to see, where there's the examples. Sometimes, of course, your f prime is going to be when f prime is undefined, that doesn't, even when your f prime at the exact point is undefined, if the neighborhoods are defined, it will still imply a local maximum. However, sometimes, it's possible, like this example here, okay, the one in the middle, where you have sort of a stop. That is like this. Your mountain has a level spot where f prime is 0 because the slope is 0 at that one spot. But then the f continues to increase. It doesn't increase, 0, decrease, increase, 0, then increase again. At that point, that is just it's just a stop. It's not a maximum or minimum. So that about covers this information, which is called the first derivative test. The first derivative test simply says if the sign goes from positive to negative at the critical point, then it is local maximum. The other way is a local minimum. If it has the same sign, then it's this situation. Okay, if the f prime is positive, 0, then positive again, or the other way, negative, 0, negative again, then it is neither a local maximum nor a local minimum. So, now having said that, so you can see that to use the first derivative test, you're given a function, you're giving some points maybe, or you're just told to find the point itself. Well, you're usually giving some points. Then you just test the value of the f, take the derivative, then test the value of the derivative on both sides and see what the sign is. Is it positive or negative? So as you can see, using the first derivative test is pretty straightforward. You just follow the recipe and out comes your result. Now you might wonder, why are we doing this? Because I can think of a quicker way to know if it's a local maximum or minimum for a given function. You just type it into the Desmos graphics calculator, or even your TI something 84, and it will, you see the graph and you know exactly what is local maximum, minimum, whatever. You don't have to do this. And the reason we have to do this is because first, it gives you a feeling of what the derivative means, and secondly, it's because this is tradition. This is these tests, the first derivative test, it was designed back in the good old days when there was no graphics calculator. So that was just about the only way you can do it back then to know if something is a local maximum. All right, so having said that, please do for your homework example 4.17. Very straightforward. You check the points and plug in some numbers, see if it's positive or negative, and then decide, following the test rules, whether your point is maximum or minimum. The same as example 4.18, which looks more complicated. Well, it might not be though. But in any case, yeah, do that one too. As again, it's just a matter of figuring out if something's positive or negative. Next, concavity. Now I'm on page 395, where we're talking about concavity. What is concavity? Concavity basically means there are two ways. Sorry, there are two ways of doing things. Let's say f is increasing. Okay, over right now we're considering f increasing in a certain interval. Now, how is it increasing? There are two ways. Well, maybe more than that, but there are, generally speaking, two ways to increase. In a short little interval, the f is either increasing this way or increasing this way. Now, increasing this way means the increase is slowing down. It's still increasing, but it's slowing down. Whereas increasing this way means it's increasing and going and getting faster and getting more and more. The increase is getting better. So this thing is called concave up. Okay, and maybe it's better if I stand on this side. This is called concave up. This is called concave down. Yeah. So you can imagine your hand here. Concave up means the increase is getting better. Concave down, the increase is dying off. It's still increasing, but it's dying off more and more. So that's the concave up and concave down business. Next, what happens is, what is concave up exactly? Well, exactly, the concave up means that the increase is increasing. In other words, the second derivative is going up. That is, this is concave up if the double prime, f, the second derivative, that is, you take derivative and then take derivative of that. The second derivative is going to be the acceleration, that is, this is bigger than 0. And in this situation, this is less than 0, okay? Because while your function is increasing, the rate of increase, that is slowing down. So the second derivative is actually less than 0 for this situation. And that's the test of concavity. The test of concavity can also be used to determine if something is a local maximum or local minimum. Because if this thing is concave down, okay, so therefore it is a maximum. That thing is concave up, therefore it's a minimum. And that is what it means. And then of course there's sometimes we have that situation. And it doesn't have to be level either. Sometimes the situation is not even level. See, it turns, the rate of turn changed right about here. See, it's concave up here in this part and then concave down on this part. So this is called the point of inflection, the inflection point. Yeah, okay, just so you know that that's the inflection point. It changed in the direction, the rate that is going. That is, it used to go concave up, and now it decides to go concave down. Now the test concavity is similar to what we did before. You find a point and test it. So that's example 4.19, and please do that for your homework because that is straightforward. And then, yeah. And after that, then you can these kind of tests. Again, let's see. Should we prove the proof of the second derivative test is? Well, I already mentioned it. It's also by corollary 3. Should I mention the proof? Yes. Okay, the proof of the second derivative test, it also follows from corollary 3, but in this case, we're arguing like this, okay? Now first, let's say f double prime at a certain point equal to 0. What does that mean? That means that what am I saying? No, it's less than 0. Sorry. We're proving a certain case. Let's say f double prime is less than 0. If it's less than 0, what does that mean? And then and also f prime at a equal to 0. That is, this is a critical point. And then that means that f prime is going to be wait a second. Okay, so by corollary 3, I will write that down. By corollary, I'm missing some letters. Okay, so I will simply write it like this. By corollary 3, that means f prime goes from bigger than 0, okay, then to f prime equals to 0, and not a. I mean before that. So f prime is it goes from the negative, goes to 0 to from bigger than 0 to 0 to negative to less than 0, which means that f prime is a decreasing function. So f prime is decreasing. Therefore, we conclude that f prime is bigger than 0 if it's for x less than a, and less than 0 if x bigger than a. And using the first derivative test, it it means that the function has a local maximum. Well, this is easier to understand than for me to explain. So please, this is on page 399. So please just read this sentence and we'll be done with it. So the point is, the second derivative test, it means when f double prime is bigger than 0, then f has a local minimum. And when it's less than 0, it has a local maximum. And that's about it. And again, this is a very straightforward thing. So let's so please do example 4.20, 4.20, and where you will check the second derivative test. The the purpose of both the first and the second derivative test is just so that we can check the local maximum or minimum with or without a graphics calculator. So please, for the homework, it's on page 403. Please do problems 201, 205, 9, 15, 19, 21, 25, 29, 35, 41, 43, and 47.